Atomic Absorption Spectroscopy, AAS. AAS is a useful technique to analyze metal, and it is highly sensitive to detect the metal in a very low concentration, the ppm level. Student, please pay attention. AAS is to test metal, not the non-metal. The word AAS, Atomic Absorption Spectroscopy, the atom will absorb a spectrum, a wave frequency. The theory behind it is like this. It says radiation is a form of wave energy. And when this wave energy hits the atom will be excited and it will jump onto a higher orbit to absorb that wave energy. What's meant by that? Now let's look onto the graph. In an atom, electron orbiting an atom, that electron have energy to orbiting an atom. So, wave also is a form of energy. The radiation wave also is a form of energy. What happened this wave hit an atom like this? So now this energy hit this electron. Now the atom is excited and the electron will jump to a higher orbit. And so this energy is passing from the radiation wave energy and pass on to the electron. And now electron will use the energy to go onto the higher orbit. And how about the energy now? This energy is absorbed. So this is this AAS theory behind. Radiation is a form of wave energy. When wave energy hit an atom, the atom is excited. Its electron will jump to a higher orbit to absorb that wave energy. Now let's look onto another picture of an atom. In case if radiation hit onto an atom, this atom will be excited. And by the look of it, you can't see much different. Look like the wave radiation pass through an atom. And when you're analyzing the wave, you will notice certain difference. The difference is when you analyze the wave, you find certain wave frequency disappear. Certain wave frequency disappear after it passing the atom. The reason is I will ask why this wave frequency disappear. The answer is because the atom absorbed that frequency. It absorbed that wave energy. So this is this atomic absorption spectroscopy about. And each metal will only absorb a characteristic of wavelengths, this spectrum, or we call spectrum. So on to the example we just said. In case if we have a different frequency, a different wavelength to hit onto an atom, what will happen? Now let's see at the second picture. Now, this atom, if you have a different frequency, different wavelengths to hit this atom, now you see nothing happened. The wave frequency, they simply passing through the atom, is they don't seem to see each other. So nothing will have this absorption take place. And what happened in another frequency? Again, at a different frequency, this atom will not absorb to jump onto higher orbit. So each atom, each metal ion will only absorb a characteristic wavelength. So, and by knowing the specific wavelengths that you absorb, you can identify the metal ion. So each metal ion in the periodic table will only absorb its specific wavelength frequency. So A wavelength frequency will absorb by A metal. B wavelength frequency will only absorb by B metal. C wavelength frequency will only absorb by C metal. So if you know that frequency being absorbed, you know must be that metal. So we call it like a fingerprint. If because that wave frequency absorbed, it must refer to the same metal. So on this example, here you show the wave frequency absorbed at here, here, and here. And of this characteristic frequency being absorbed, this you can identify it is a sodium. That's we call this AAS is so specific, it can only absorb its own type of frequency. The experiment is like this. First of all, each metal you have required to have a special lamp to generate that frequency. And each lamp will generate one type of frequency. So you have to identify your experiment, what metal you're testing, before you go to the library to borrow the lamp. You cannot ask for, can I have all the whole periodic table lamp? They're not going to give you. You ask for a specific lamp. I want the lamp to test for lead, or I want the lamp to test for zinc, like that. So once you require, each metal require a special lamp, so that lamp will generate that frequency. So you identify the metal first, and then you go get the lamp. Now next step, you spray the sample onto the flame. Those unknown sample that you're testing, you spray it onto the flame. Why? So that it will become vaporized. So it become a vapor of atom ion. So it become vapor. Then, second step, you're using that lamp to pass the light beam through. You're using that lamp to pass the light beam through the sample. Then the elements will absorb. The element will absorb that frequency of light because of that specific wave frequency will absorb by the atom. And by counting for the frequency of that light absorbed, it's going to be analyzed by the detector. and the detector will read out how much being absorbed by the sample. AAS, they have many applications. For example, the pollution in the air, water, soil, like in case if you're in a heavy traffic area, you would suspect, does the air contain lead or any heavy metal? Agriculture, farmer, when they fertilizing the crops, they have to know the soil. Do they have enough mineral? Do they have enough zinc or copper or iron? Or would it be too much? They have to identify before they fertilize the crops. Mining industry, they have to know, does the rock or the ore have sufficient mineral worth extracting? On the food that you drink, like the seafood, oyster, mussel, tuna, they all can absorb heavy metal. So especially those deep sea fish. So they have to be constantly testing, would the deep sea fish contain heavy metal which will affect our health. Medical diagnosis. For the blood test, do you have enough iron and zinc or calcium in it? Or do the urine test? So all this is to identifying the metal. So don't assume AAS metal got nothing to do with you. It affects all part of your life. Now we're going to talk about the calibration curve. On calibration curve, first study what is the x-axis, mg per liter, mg per liter, the concentration unit. What's on the y-axis? Nm, which is the wave frequency unit, the wave frequency. Now let's start. You have to prepare, we aim to prepare two things. One, you're going to match the standard solution against the sample. The standard solution against the sample. This may remind you your titration. You have to match the standard solution with your sample to do your titration testing. This is a bit alike. Now let's see. First, you prepare the standard solution, the first bottle. Standard solution means you know the concentration. This known concentration, 1.20 mg per liter, is because you prepare, you know. Then you put it onto the graph. And once you put onto the graph, this is 1.20. And on the y-axis, you put this sample using the early experiment, spray onto the spray, shine the light through, and obtain the reading. And the reading will give you 0.2 nm. So now you convert this concentration into a nm by using the AAS machine. You put it onto the graph. And now the second sample, you do exactly the same. Put onto the graph using the AAS machine to obtain the reading. and then do the third time. So this sample you prepare, you know the concentration, you put onto the AES machine, obtain the reading. So now if you link it together, you will have a straight line. Start from 0. You will have a straight line. And now I'm going to using this straight line to do my sample testing. Now we go to the sample. In the sample, I have the sample obtained could be from the river or could be from the farm, from the soil, to obtain that solution. That is the sample that I want to find out the concentration of the metal. In this one, I'm testing zinc. I want to know the zinc concentration. And how do I do? Step number 1. I will using this 4 bottle, put it onto the machine, the AES machine, to obtain the NM reading. So now after I do it 4 times, I have the NM reading for each bottle. Then I average it. I get the average. Now this gives me the mean value, the mean concentration of the sample, 0.64 nm. Now I'm going to using this number, put it onto the calibration curve and project like this. So I'm using this number project onto this straight line from the standard solution that we draft. Now you read, here is the value. Now what I'm pointing, the mg per liter. So this 0.64 nm, the value is 3.70 mg per liter. Now I convert the nm into mg per liter. Student, please understand this step.